Right, we're diving deep today, and this time it's into evaluating agent-based program repair at Google.
Oh, yeah.
You shared this one with me, and knowing your interest in machine learning, I figured this would be right up your alley.
Definitely a hot topic, yeah.
Yeah, so let's unpack this a little bit. So this paper, it tackles this idea of using LLMs to automatically fix bugs in code.
Right.
Specifically looking at like massive code bases like Google's.
That's right.
So this is kind of it's a big step forward in automated program repair.
Definitely.
So this is kind of like having an AI coding buddy who can not only spot those errors, but actually suggest fixes. Right?
Yeah, exactly.
Pretty cool.
And they don't just talk about the theory in this paper. They actually built an agent called Paserine.
Okay.
And they tested it on 178 real bugs from Google's internal issue tracker.
Whoa. So they actually used real bugs.
Real world bugs.
At Google.
Yeah.
Wow, that's a serious challenge.
Definitely.
So, this paper, kind of in the broader context of automated program repair, where does this fit in?
So, we've seen a whole evolution of approaches to this problem.
Okay.
Early on, it was all about statistical methods.
Yeah.
Then deep learning models came along.
Right.
But they were focused on specific tasks like finding where the fault is or generating the patch to fix it. And now we're starting to see these agents that can handle the entire repair process, from start to finish.
So taking it from end to end.
Exactly.
Okay, so tools like SWE agent, autocode rover, repair agent. These have all kind of shown that LLMs, when you integrate them into an agent-based system, you can take that bug description and they can autonomously generate tests, pinpoint the problem, suggest the fixes, validate those fixes, and even submit the solution.
Yeah, exactly.
It's kind of like pair programming, but with AI.
It is, yeah.
But most of those, if I understand correctly, they've been tested on open source bugs, right?
That's right.
And specifically the SWB bench data set. That's what makes this Google paper so interesting, because they're like, okay, can we apply this to this massive, diverse code base that Google has?
Exactly, yeah. It's completely different than working on open source projects.
I can imagine, yeah.
Completely different.
So how did they...
So to do that, they had to create a relevant and challenging evaluation set by carefully filtering through thousands of bugs.
Oh, wow.
From their internal issue trackers.
So not just any bug.
No.
They had criteria.
Exactly. They focused on bugs that had clear fixes, testable code that could realistically be handled by an AI agent in its current form.
Okay.
They ended up with 178 bugs split between those that were reported by humans and those that were flagged by automated systems.
Oh, that's an interesting distinction right there.
Yes, absolutely.
So we've got those human-reported bugs. We've got these automated ones.
Right.
I'm guessing those present different challenges, right?
Absolutely. Yeah. And within those machine-reported bugs, they actually divided them into bugs that were found by automated sanitizers, which catch things like memory errors.
Right.
And those that were flagged by a test order dependency analyzer.
Okay, so we've got a variety
of bugs
to really put Paserine to the test.
That's right, yeah.
So we've got these Google bugs, right?
Yep.
How do they compare to the ones that we normally see in these open source data sets like SWE bench?
Yeah, that's a great question.
Or are they similar in complexity?
So that's one of the key insights from this paper.
Okay.
They found that the Google bugs were often more complex.
Oh, wow.
Involving changes across multiple files.
Okay.
The fixes themselves were more spread out within those files. Okay.
And the bugs affected more lines of code overall.
So it's like a quick patch versus major surgery.
Exactly.
Yeah.
And when they analyzed the bug descriptions, they found another interesting difference.
Good.
Google's internal reports often contain fewer code-related terms.
Oh, really?
Compared to the open source bug reports.
So that would make it tougher, I would imagine.
Oh, yeah, much harder.
For Paserine to kind of figure this out.
Exactly.
So, all right, we've got the context. Yeah. We understand the challenges.
Right.
Let's talk about Paserine itself.
Okay.
How does this AI agent actually work?
So they kept the design intentionally simple.
Okay.
They drew inspiration from SWE agent, and it basically follows what they call React loop.
react loop.
Okay.
Yeah, can you explain that a little more?
Yeah, what is that?
Sure. Essentially, it's a cycle of thinking, acting, and observing. In the thinking stage, the LLM generates a natural language explanation of its current understanding of the problem and then decides on an action to take.
Okay.
And that action is basically like a command to execute.
So it's kind of
like it's thinking out loud?
Yeah, like the AI is like, okay, I'm going to try this.
Exactly.
Okay.
And then in the observing stage, it analyzes the output of that command, which could be anything, from the contents of a file to the results of a test.
Okay.
And then that information feeds back into the loop to guide its next step.
So it's constantly kind of learning?
Yes, yeah.
And refining and...
Continuously learning.
So to interact with Google's environment, they had to give Paserine a small set of commands.
Yeah, like things like viewing files, searching the code base, editing code, running tests, and then signaling, when it thinks it's finished, the repair.
So very kind of focused set of tools there.
That's right.
Was that for any particular reason, like safety or...
Yes, absolutely, for safety. Make sure it can operate effectively, but also stay within, safe boundaries.
So, okay, we've built this AI agent.
Right.
We've got this set of real-world bugs.
Yes.
We've given it this limited set of tools. What was the setup for the evaluation?
Okay, so...
How did they test Paserine on these bugs?
They started by, setting up the environment, loading the bug information and checking out the code from the repository as it existed before the bug was fixed.
Okay.
And they confirmed that the bug actually existed in that version of the code.
So they're recreating?
They're recreating it, exactly. So it's like a controlled experiment.
Right, okay.
And then Paserine takes over, runs independently, but leaves a detailed log of its actions.
So they can analyze it?
Exactly, yeah, for later analysis.
Gotcha.
And crucially, they made sure that during the execution, Paserine had no access to any information from the future.
Oh.
No peeking at the actual fix.
So it had to figure it out itself.
Yeah.
Based on what it knew.
That's right.
At that point in time.
That's right.
Okay, so we've got the bugs.
Right.
We've got the AI agent.
Yeah.
We've got the tools. We've got the evaluation framework.
Right.
How do they measure its performance?
Right. So they focused on two key aspects.
Okay.
Patch correctness and what they call trajectory dynamics.
Okay, what is...
Let's unpack those.
Yeah, let's unpack those.
Okay, so patch correctness.
Yeah.
They make a distinction between plausible patches and valid patches.
Okay.
So a plausible patch means that it makes the bug reproducing tests pass.
Okay.
But a valid patch goes further. It has to be semantically equivalent to the actual human written fix.
Oh, wow. So a plausible patch might fix it, but...
It might just be a workaround.
It might just be a workaround, yeah.
Yeah, whereas a valid patch is like, no, this is the correct solution.
Yeah, it's like really understanding the underlying problem.
Exactly.
And coming up with a valid solution.
Yeah, and to determine validity, they had to manually analyze the patches.
Okay, that makes sense.
And then trajectory dynamics.
Yeah, trajectory dynamics.
This refers to the sequence of commands that Paserine uses to arrive at a solution.
Okay.
So they looked at how efficiently it localized the bug and whether there were any signs of inefficient or unusual behavior.
So not just did it get to the answer?
Right. It's about the process.
It's about how it got there.
Exactly.
Okay. So evaluating a chess player's strategy.
Exactly.
Not just whether they won or lost.
Exactly.
So how did Paserine actually do?
That's the big question.
Yeah.
Yeah. The results are quite interesting. Well, the results are quite impressive, actually.
Oh, really?
Yeah. Paserine managed to create patches that passed the tests for a significant portion of the bugs.
That's good.
It was 73% of the machine-reported bugs and 25.6% of the human-reported bugs.
Okay, so that's pretty good.
Yeah.
Considering
the complexity.
The complexity and the fact that it had these limitations on the tool.
That's right.
Okay.
And then when they dug deeper and looked at the validity of those patches, they found that for 43% of the machine-reported bugs and 17.9% of the human-reported bugs, Paserine had actually generated at least one patch.
Wow.
That was semantically equivalent to the ground truth fix.
So it wasn't just finding workarounds?
No, it was actually understanding
the
problem and coming up with the correct solution.
That's awesome.
Which is really remarkable.
Yeah.
And one of the most fascinating findings was how Paserine's approach differed depending on the type of bug.
Oh, so it adapted.
It adapted
based on the information available.
Exactly. Yeah.
That's cool.
So for human-reported bugs where, those bug reports often lacked detailed, like, code-related information, Paserine spent more time, like, exploring the code base, searching through files, trying to understand the context.
It's like it had to do more work.
Yes.
On the human-reported ones.
Yeah, whereas for the machine-reported bugs, which often came with, like, clear instructions on how to reproduce the error.
It's almost like it had a senior developer telling it, here's what's wrong, go fix it.
Exactly, yeah.
Okay, interesting.
So it could just jump right into, like, testing and editing.
So that actually, has implications for how we might
absolutely
report bugs, right?
Yeah.
Going forward.
So,
for these AI agents,
if we can encourage developers to provide, like, more structured, detailed bug reports.
So this idea of clear, structured information seems to be key.
It's key.
For these AI agents.
Yeah, and they found other evidence to support this.
Oh, really?
They looked at something called the file system distance.
File system distance.
Which basically measures how close the files edited by Paserine were to the actual location of the bug fix.
Okay.
And they found that for machine-reported bugs, even in cases where Paserine didn't produce, like, a plausible patch, it was still more likely to pinpoint the correct file.
Interesting.
Compared to the human-reported bugs.
So even when it wasn't successful, it was still kind of on the right track.
Yeah, it was getting closer.
Because it had...
Yeah, because it had better information.
Better information, okay.
Exactly. Now, of course, with any new technology,
there are challenges.
There are challenges and limitations to consider.
Sure.
One of the biggest hurdles that they encountered was the issue of context size.
Ah, you're talking about...
Yeah, the working memory.
The working memory of the LLM.
Of the LLM, exactly.
Yeah, okay.
With all those code files and test results and logs being fed into the LLM. They sometimes ran into situations where the prompt exceeded the model's maximum context window.
I can imagine.
Even with very large models.
Yeah, it's like information overload.
It is, yeah. So they're exploring ways to address this limitation, like using a sliding window to just focus on the most recent interactions, or even using another LLM.
Whoa, an LLM to manage an LLM?
They summarize the history.
Okay.
Yeah.
That's wild.
They're pretty wild.
Okay, so what other challenges?
Another significant challenge was the bug reproduction process.
Okay.
Particularly for those human-reported bugs.
Yeah.
As we discussed, the machine-generated bugs often came with, like, clear steps on how to reproduce the issue.
Right, like a recipe.
Exactly.
Versus just like, make this dish however you want.
Exactly.
Yeah.
And so for the human ones, it was more of a guessing game for Paserine.
Yeah.
And so this sometimes made it difficult for it to even trigger the bug. Let alone fix it.
Right.
So that's why they're working on a separate project to explore how agents can generate those bug reproducing tests.
So that would be huge.
Automatically.
Yeah, because then they can kind of like set it at their own crime scene.
Exactly.
And then be like, okay, here's what happened.
Yeah, that's a great analogy.
Okay.
They also noted some areas where Paserine's performance could be enhanced.
Okay.
With, like, a more sophisticated set of tools.
Right.
For example, they observed that the agent sometimes tried to use commands that weren't available to it.
Okay.
Like a print command to, like, ask the user for more information, even though there's no interactive capability.
Like trying to call for backup when you don't have a radio.
Exactly. And so, they're already planning to expand Paserine's toolkit.
Makes sense.
Based on these observations, it's exciting to think about the possibilities. Maybe someday these agents will be able to access documentation, search the web for solutions, or even consult with human developers directly.
Wow, now that would be
a game changer.
Yeah.
Yes.
Speaking of areas for improvement, how did Paserine do when it came to fault localization?
Right. So
especially on those tricky human-reported bugs.
That's another area where there's room for improvement. So currently, Paserine doesn't have, like, a dedicated localization phase.
Okay.
It just relies on that dynamic loop to figure things out.
Okay.
And they acknowledge that this can be inefficient, especially for, like, complex bugs.
For those complex ones,
Yeah.
Okay.
So they're exploring ways to incorporate more sophisticated localization techniques, such as, like, the iterative code search approach used in AutoCode Rover.
Yeah.
They're also looking at how to leverage the vast development history available within Google,
Yeah.
which could provide clues about like similar bugs.
Like a case database.
For bugs.
Exactly.
Okay.
Now, another limitation they mentioned
Yeah.
is the lack of diversity in the patches
Okay.
generated by Paserine. So currently, it samples trajectories independently, which means it might miss out on exploring potentially better solutions.
Okay.
So they're looking at like more advanced techniques like beam search and conditioning the LLMs generation on like previously explored patches, which could lead to
more diversity,
more diverse and higher quality solutions.
Yeah, it makes sense.
So it's all about helping these AI agents become like more strategic in their approach.
Right. So not just like throw stuff at the wall and see what sticks.
Exactly.
Yeah. Okay.
Now, before we move on to our novel notions segment, there's one more important deployment consideration they discussed.
Okay.
The idea of abstention.
Abstention. Yeah. So like choosing not to participate.
Yeah. Basically, they recognize that in a real world setting,
Paserine will inevitably encounter bugs.
Right.
That are just beyond its capabilities.
Yeah, it's like calling the FBI when it's too complex, right?
That's a great analogy, yeah.
Okay.
So they're working on ways to teach Paserine to recognize when it's unlikely to be successful and to just abstain from attempting a repair in those cases.
That makes sense.
Save time and resources.
Right, like humans can work on the hard ones.
Exactly.
Let the AI do the easy ones.
Yeah. And that brings us to our novel notions segment, where we take the insights from this paper and let our imaginations run wild.
I always love this part of the show.
So this paper really got me thinking about the future of bug prevention.
Oh, okay.
Like, what if we could train these repair agents, not just to fix bugs, but to anticipate them as the code's being written?
You're talking about predicting bugs before they even happen.
That's exactly what I'm talking about.
That's what?
It's pretty wild.
Okay.
Yeah, imagine an AI that analyzes code as you write it and flags potential issues before they even arise.
Like a coding buddy.
Yeah.
Who's also psychic.
Yeah, that's a...
like a psychic debugger.
That's a vivid image.
Okay.
Yeah, but think about the potential.
Okay, I'm intrigued. So how would we, like realistically, how would we even begin to develop something like that? So how would we, like realistically, how would we even begin to develop something like that?
Well, it would definitely require a whole new level of sophistication in our machine learning models.
Okay.
We'd need to train these models on like vast data sets of code, not just bug reports, to help them understand like the intricate relationships between different parts of a code base.
So not just here's a bug, here's the fix.
It's not enough. They need to understand how code is structured, how different components interact, and how seemingly minor changes can ripple through a system and cause unexpected issues. And they'd need to be able to analyze code in real time as it's being written, flagging potential vulnerabilities or logical inconsistencies.
So before they even become like real bugs?
Before they even become bugs, exactly.
I mean, that sounds like a monumental task.
It is.
I mean, is there anything...
It is a huge challenge.
Is there anything that exists that we could adapt?
So there are some promising avenues to explore. For instance, we could leverage techniques from natural language processing to like analyze the semantics of code. Essentially understanding the meaning behind the code, not just the syntax.
So instead of just looking at like, okay, here are the instructions, it's like, what's the intent?
What's the intent?
Behind it.
Exactly. And by understanding the intent, they could potentially identify situations where the code's logic deviates from the developer's intended outcome.
Even if the code is correct.
Even if the code itself is syntactically correct.
That's really cool.
Yeah.
So it's almost like
it's reading your mind.
Yeah, it's like, wait a minute. This isn't going to do what you think it's going to do.
Exactly, yeah.
Wow, okay.
And we could also draw inspiration from other areas of machine learning. Like anomaly detection, where models are trained to identify unusual patterns or deviations from the norm. So in the context of code, this could involve training models to recognize code patterns that are statistically likely to lead to bugs.
So it's like learning from everybody who's made all these mistakes before.
Exactly.
Okay.
And as these models analyze code, they could provide real-time feedback to developers. suggesting alternative approaches.
Right.
Highlighting potential pitfalls.
So it's like
a virtual coding mentor.
Yeah, like a coding mentor.
Looking over your shoulder.
Looking over your shoulder, yeah.
Giving you hints, yeah.
That's really cool.
Now, there are obviously many technical hurdles to overcome.
Right.
These models would need to be incredibly sophisticated and robust
to handle
the vast complexities of modern code bases, but
the
potential benefits are enormous.
A world with no bugs.
Imagine a world where bugs are caught
right.
and corrected before they even have a chance to wreak havoc.
That would be amazing.
Yeah, it would be a revolutionary shift in software development,
This has been a truly mind-expanding kind of exploration of
it's really fascinating.
AI in software development.
Yeah.
From fixing these bugs to
preventing them,
predicting them before they even happen.
It's really cool.
It's amazing.
Yeah, it's a rapidly evolving field.
Well, that brings us to the end of our deep dive into evaluating agent-based program repair at Google. And, hopefully you enjoyed this journey into this world of AI-powered bug fixing.
Absolutely.
And kind of this, look into the future.
A glimpse into the future.
Of bug prevention.
Bug prevention,
Really cool stuff.
It is,
So keep those minds curious.
Yes.
And those imaginations firing.
Absolutely.
Let's see you next time.
Until next time.